Welcome back. So we'll continue for our meta-analysis of binary outcomes. And as I said in the previous session, odds ratio, if you have odds ratio or risk ratio, you're going to use metabin. And the metabin function will help you pull or calculate the risk ratios and also the standard errors. And at the end, we'll be able to meta-analyze them together. But sometimes the studies may report just risk ratio, odds ratio as it is, without the number of events and the number of events in the experimental, in the control group, or maybe in the exposed group and then non-exposed group. You may simply have the population, the number of events, rather than the odds ratio. So that means you will have to pre-calculate the effect sizes using the metabin. You will have to calculate using metabin. It will be able to calculate the odds ratio and the risk ratio. But sometimes studies may report just the risk ratio without the number of people. So that then you have to use the metagen function. Especially if they, most commonly they report risk ratios or odds ratios and 95% confidence interval. So you can use a point estimate odds ratio and the 95% confidence interval, the lower and upper bound, and then metagen will help you pull them together. Yeah, so for today, these are the packages that I need. I use Meta4. I just load it in case there are some functions that Meta is built on. So sometimes Meta is using some of the functions in Meta4. That's why we will have to load both of them together. And there is dplyr. As always, we may do some data manipulation, and for that we will need to use dplyr. So I will just run this, and as I said, the data is coming from this paper, and one of the authors made the data available for us. And here is the data. The data that we need is this data 07. This is what I need. This is a CSV version of the data set. So I will simply copy this link, and then I will call this data set as df read CSV, and then I will simply paste that link, and I will be able to read the data set. So now it's already read. We will take a close look at how this data look like, and this is how this data looks like. So we have a number of studies. Studies. The name of the study is like the first name, the first author, I believe. The first name, last name of the first author. And then you have the number of events in the experimental group and total number of events in the control group. No, this is not total number of events in the control group. Rather, the sample size in the experimental group, and this is the sample size in the control group. This E are the number of events in the experimental group in this case, and then in the control group in this case. So that's what we need for the meta-analysis. Before we do meta-analysis of this, what we need to know is, you remember, last time we were also talking about this skewed distribution. This, for example, correlation is between -1 and 1, always between this. So its correlation value is skewed within this range. It doesn't go beyond 1 or less than -1. So that's why it's skewed within this range. So that's why we used for correlation, if you remember, we used the Z-port transformation. And for odds ratios, again, odds ratios are always between 0 and 1. Between 0 and infinity. So it's between 0 and infinity, always from 0. It never goes below 0. So that's the nature of odds ratio. It's always from 0 to infinity. So that's why you will have to transform the odds ratio. Especially if you are pre-calculating odds ratios, then you will have to transform them. You will have to transform so that they will be log transformed, and they will be, and with that you will be able to pull them together. Otherwise, the pulling will not work for you. So that's how it looks like. If you remember last time, we have already we had these formulas. So this is how odds ratio is calculated: number of events in the experimental group divided by the total number of events and non-events. So that means the total number of events. Sample size minus the number of people diseased group. That's how you calculate it. And if you take the ratio, that's how you calculate the standard error. If you remember this formula, 1 over A plus 1 over B plus 1 over C plus 1 over B, you take the inverse of all. Here, you take the inverse of all of these events, and then all of this, you take the inverse and you put them in square root, and then you get standard error. That's how you calculate the standard error. So you take this reciprocal, and then that's how you calculate standard error. So let's say let's take one study, and let me calculate one standard error. That's actually how you calculate standard error. Let me just calculate this. So I take with function, and I take the data frame, and I'm filtering for Kaiser for this. Let me calculate just the standard error. So it's the standard error. That's how the standard error looks like. Otherwise, you can also round it. You can round it into, I don't know, 3 digits or something. But I'm not doing that now. But let me also let me try to calculate odds ratio. As I said, odds ratio is calculated this way. The way you calculate odds ratio is here. So we have here. So that means I'm simply copying this formula in here. So it's like E over NE minus EE, and then you have the EC, and then I'm passing it by log, because I want to calculate the log odds ratio. So if I run this, I get the log odds. Actually, if you exponent this number, so that means you get the coefficient, the odds ratio itself. That's the log odds, and this is the odds ratio. So that will be the odds ratio that we at the end see in our plot, in our meta-analysis plot. But that's how you calculate the odds ratio. So that means we have this data. For this, we don't need anything else. We have everything that we need. We simply plug in. We will simply call our function. That's a metabin function, and then we actually we can we can actually calculate the log odds ratio, so that because I'm going to show you two different methods. That's the metabin and the metagen. So the metagen, we will probably see it better. I think it's better to divide this video into two. Maybe we take the metabin, and then later in the next session we will talk about metagen. We will talk about metagen. But for that, I think it would be a good idea to calculate also the pre-calculated effect sizes like log odds ratio, and we can also calculate lower upper bound, lower bound, and also standard error. We can simply do that, and I think that for that, let me use df, that means the data frame I have, and let me use mutate this declare function, and then let me call this log odds ratio, and then after that I will simply call this formula. Where is it? This one here. This one. That's what I need. So let me call that here log odds ratio, and then let me again calculate the standard error. The standard error is calculated by that formula again. This is square root of this one here. So I'm simply copying this here, and this one here. So I'm copying this here and dropping it here. And the next one is I want to calculate the log lower, actually the logarithm of lower bound. That means the lower side of the 95% confidence interval. Of course, the log odds ratio. So that one, I think you know the way you calculate the 95% confidence interval is like you have the estimate plus or minus 1.96. 1.96. That means this is a standard normal distribution at the alpha over 2. That means 1.96 times the standard error. That's how you calculate the confidence interval. So because we are doing the lower bound, for that I can call my log OR, my log odds ratio minus, let me put this in 1.96 times standard error. That's what I need. And then the next one, I will use the upper bound. That means the log upper. Let me call it log upper, and then that will be log odds ratio plus this one, as it is. Let me bring that one here. And I don't need another thing. So now I can simply rerun this, and then I will be able to see that how the data looks like. Let me see how DF looks like. And now I already have the log odds ratio, the standard error, and log lower and log upper. So I have everything. I can use either metabin or either metabin or metagen function. So for this video, I will just use metabin, and for the next one, I will just use metagen. So for the metabin, what we need is actually these values, all of these ones according to the order. That's all you need. You don't need anything else. I will simply take these ones, and then I will simply call my metabin function. Let me call it model 1, and then metabin times for metabin, and then these are the arguments that I need. So let me just call this into yeah. So let's let me just move them here. There's a lot of space here. Actually, it was fine. So I have all. Actually, this, if you look at the metabin function, it needs to be in this order. That actually metabin also tells you it's just the function. Actually, let me just display that as always. You can simply ask, and I mean, in other studio this would be easier, but. So these are how they are. So in event E, so the first one has to be event E, and then the next one is NE, and then event C and NC. After that, we have multiple different arguments, but I will not go into the details. Let me just simply use the method. What we're going to use today is the inverse variance, because as I said in my previous session, if you want to reproduce what other people have done, especially, I mean, many people use Stata, or maybe, especially in this case, they use Raveman. So we want to reproduce that. Usually people use inverse variance, but if you are using R, then you can use other advanced estimators, advanced methods. So the data is DF, and then let me define my effect size measure. The association measure is odds ratio. And then after that, I can also define the student lab. So in my forest plot, it will be clear. So for that, I will simply call study. Now I should be able to run study actually. So this should work. Let me hope. Yeah, it did. And let me call, maybe if you want, you can simply call forest M1. So you can have a look how the forest plot looks like using the metabin function. Yeah, all right, we have everything here. So you'll see we have the studies. Here are the number of like the people in each, like in the events total. Yeah, and then we have odds ratios. These are already calculated. So yeah, so it's giving us odds ratio, and then the weights. Yeah, also it's giving us the common effect model. That means the fixed effect model and the random effects model, and it's giving us the weight. But I don't want to see the fixed effect model. I just want to use random effects model. So I will turn this to false, and I will simply use random effects. In fact, it's not recommended to use fixed effect model unless you are really replicating the same study in the same population, just different times. So it's still, you know, there's always heterogeneity. So it's not really. I mean, people use this I square value as a cut point, or tau square sometimes, but it's not really worth to use a fixed effect model. I mean, in the end, actually, if I square is close to 0, the fixed effect model, or whether you use fixed effect or random effect, it won't make a difference. It will still be the same. But still, I recommend using just the random effects model. Yeah, so I just remove the random effects, the fixed effect model, and then this is how our estimate looks like. But you can also, yeah, so this is significant. It's so that means it's increasing the risk of I don't know what was that event. So anyway, it's the odds of having, with all these studies, it's showing that it's increasing the risk of, I mean, the odds of experiencing I don't know, some kind of thing, which I don't remember what was the outcome. Anyway, here is odds ratio 1.33. And then 0.91 to 1.93. I'm not exactly sure actually whether this was the odds ratio that we are trying to reproduce. Yeah, I just use the data, and I didn't read the paper actually. So if you want, you can have a look. I don't have full text access here, at least, because it's not full. Anyway, anyone who wants to reproduce this paper, you want to see which estimate we just estimated, it pulled 1.36. Remember this number. We will take a look again using metabin function. We'll have to see it again with a different way of doing it. If you remember, we already have our lunch here. We already calculated most of it. So this is our handwork, manual work, but the metabin is also doing it for us. But just for the demonstration, you can also do it this way. I will show you using this part, but just using the metabin function. I will ignore all these values. I already pre-calculated the effect sizes, because that's actually the most common. At least you don't have to, you may not pre-calculate, but at least people report odds ratio. Then for that, you will convert it in log odds, and then standard error also, you have to convert it to log what I report, and then you can pull them together. That's what you can do. So for the next one, we will use metabin. But yeah, I think yeah. Okay, so we will use the metabin function, and for the metabin, we will use only these ones. Yeah, I think yeah, that's it. Next time, see you next time. Thanks.